Okay, so in this video, we're just going to go over some of the basic definitions in graph theory that will basically help us talk about graphs in a bit more standardized way, right, when we go into the more complicated material. And you've already seen two of these terms, right, vertices and edges. So the vertices are visually these points that you can draw like this, and can give them names A, B, C, and D, right? It's a finite set of elements. And E in your graph, these are your what we call edges, which are unordered pairs of elements. And so I can have the graph edges like this, for instance. And in this case, E would be the set containing AB, AC, BD, and CD. Right, so that's what a graph is. Also, I just want to mention some other notation here in relation to edges of the graph, right? So if AB is an edge, right? So we would write AB in the set of edges. Then we would say that A is an endpoint of that edge, right? So sometimes we do give names to edges as well. So we can call this edge E, for instance, right? And we say E equals AB. It's in capital E to denote membership there. So we're just going to say A and B are endpoints of that edge, right? Kind of like endpoints of an interval, right? But here it's an edge. We will also say A and B are adjacent to each other, right? So as vertices, they are adjacent if there's an edge connecting them. Finally, as a counterpart to being endpoints, we will also say E as an edge is incident to the vertices A and B. Right? And so incident and endpoints, that's just sort of like the reverse definition of one another, going from the vertices to the edge or the edge to the vertices. And then again, two vertices are adjacent if there's an edge between them. So just to give you another example here, we would also say B and C are not adjacent, right? Because there is no edge in between them. A few more definitions here that might be relevant for some of the topics in the course is that of a simple graph versus that of a multigraph. And the main difference here between the two is whether E has repeated elements or not. Right, and so in the graph that I drew on the previous slide there, it was A, B, C, and D. This is a simple graph because between any two vertices, there is at most one edge. Right? So if there's already an edge from A to B, then you can't have any more edges from A to B. Right? So if you, again, write your set E in that case, it will simply contain each edge once. Whereas if I were to draw the same set of vertices, A, B, C, D, and instead have something like this, right? So now this is something that's called a multigraph, because when you write out your collection E of unordered pairs, AB is there twice, because there are two edges in between A and B. And then AC, and then CD, and CD. Right? And so really another name for this, if you remember, is that this is a multiset. Right? In which case you allow elements inside that collection to be repeated. Right? And so there will be some scenarios or problems where we would like to model them using a multigraph instead of a simple graph, right? If there could be, say, more than one connection between vertices in that scenario. Usually it will be clear from the context if that specific problem you're working on is talking about a simple graph or a multigraph, Now, just as a last definition here, I do also want to talk about degrees of vertices, and in relation to the number of edges, right, for which that vertex is an endpoint. And yeah, so really this is like an incorrect notation here. We just defined the proper wording. This should be incident instead of adjacent, right? Because you're counting how many edges have V as an endpoint. So I'll give you an example for this graph. We would say that the degree of the vertex V2 is 3, because there are 3 edges connected to V2. Right? So it's really as simple as that. You're just counting how many edges there are that has V2 as an endpoint. V5 has degree 2. And so if I were to list all the degrees of all these vertices here, so V1 would have degree 2, this is 3, 2, 3, 3, 3, and 2. Then the non-increasing sequence of numbers formed by these 2s and these 3s here, that's going to be called the degree sequence of the graph. Right, so this specific graph will have degree sequence 3, 3, 3, 3, and so there are 4 vertices that have degree 3, and then 3 vertices with degree 2. Right, so its degree sequence is 3, 3, 3, 3, 2, 2, 2. And that's always going to be like a unique sequence for any given graph, right? Because the canonical ordering here is that we're writing these numbers in a non-increasing ordering, right? And so for any graph, you can pretty much get its degree sequence, right? So I'll draw another one here. How about this graph? Well, this graph has all 3s, so its degree sequence is 3, 3, 3, 3. Well, if you have a graph, say, that looks like this, right? So this is a graph. I can give labels to the vertices as well, A, B, C, and D. So you have a finite set of vertices, and your edge set is just a single edge connecting C and D. And that's perfectly fine for graphs. You can have vertices like this that are isolated from the rest, that are not endpoints of any edge. And in this case, the degree of A and the degree of B are both 0. C and D are 1, so the degree sequence here is 1, 1, 0, 0. Okay, and it's pretty easy, right? Starting from a graph, can you give the degree sequence? Like, it's literally, you just have to count how many edges are connected to each vertex. What's more interesting is the reverse question. Given a degree sequence, is there a graph with that specific degree sequence? In fact, you can also ask the question, given a degree sequence, is there a unique graph with that degree sequence? And we'll define later what unique means in that case when it comes to graphs. But yeah, maybe you can start thinking about these questions now.